Hi everybody, this is Miss Fred. We will be continuing with Cosecant and Secant. I included a graphic organizer for you in Google Classroom, so you'll find it either in Kami or as a PDF in Google Classroom. So look for that. You might want to print this out or at least copy the table, and then we'll get started. So what I've done here is I wrote out the equation just like normal, and then what I did is I reminded you that cosecant is the reciprocal of sine x. And I went ahead and just put in the skeleton for sine x, and then I'm going to go ahead and superimpose cosecant on top of it. So before I do that, I'm going to fill out this table, and just to remind you about strategies how to do that. If you've got a couple ways you can do this. This is not the way I usually do it, but if you have your unit circle, or you can just make a really quick sketch, you can see here that these are the y values, are the sine, and so you can just take them straight off the unit circle, understanding you know where that is. So I'm just going to make a table for sine x is equal to y. And these are those x values that work as the parent points. Okay, now what I do is I just go ahead and graph it and then use the graph. But I also wanted you to see how these are connected. Okay, or you have them memorized fast. All right, so now that I have that, I can go ahead and flip the values around and stick them into my table. That's why knowing the properties really saves you a ton of time. And it's quick. Okay, so I'm going to put it in green so you know that it goes with the cosecant. All right, so I have my values. I'm going to go ahead up to my graph and start graphing those items. So I'm at 2 points. That's it. That's all I got. And putting in your asymptotes. This graph is more than one period, so just keep that in mind. It's like a period and a half. But I'm just going to do the whole thing on the graph, so just keep that in mind. All right, I'm going to use those asymptotes to get the structure here. And one more. So what I did for you, if you look at your sheet, of course, is I provided you with a neater graph down in the bottom. So I will be referring back to that from time to time. All right, let's go ahead and look at that domain. So the domain are all the defined values, to remind you, for the function. And what I've done here is I've just kind of blocked off one period for you. So let's look at where is the function undefined. So I'm going to superimpose a number line up at the top. And it looks like there's 0 and then pi over 2. So the distance between those asymptotes is the distance of pi. You can see it right here, and then up from pi to 2 pi. So I'm going to put little circles there to remind you there's gaps. And so your asymptote is going to start at 0. You have a distance of pi, and then it's going to repeat because you know this is periodic. All right, next we're going to work on the range. So you can see the arrows down below, which means we are starting with the y values that head towards negative infinity. And as we move up the y-axis, what you will see is the graph will create a gap for the y's starting at -1. So this is all included in our range. And then I have that big old gap because it is the yellow part of the graph, which is sine. We don't want that. And then we're going back starting up at 1. And remember, there are points here, so define values, no holes. And so we are going from 1 up to positive infinity. So I'm going to just write that out here. in interval notation, then I'll transfer it over to the table. So I'm starting here from -1, going to -1 inclusive, union, +1 to infinity. We're going to take that information and stick it in our table. So let's go ahead and do that now and see anything else that we can fill in. So x cannot be, because this is the domain, starting at 0 and then pi k. K is an element of z. And then the range was from -infinity up to -1 and union 1 to infinity. All right, so you can see now because of the asymptotes, we have a discontinuous function. There are breaks. And because this is the reciprocal graph of sine, let me go ahead and put that in with highlighter for you. We have an odd function again. So it's going to behave the same way as the reciprocal. Remember, this is symmetric through or about the origin. Let's look at the maximums now. So I actually don't need to go to the big graph for this. What you need to keep in mind for the maximum values is we have arrows here. So we're never going to reach the highest point on this graph. We're going towards infinity, so there's no maximum for this one. And then likewise, no minimum on the bottom because of the arrows. So there is no minimum. So that's cool. That's over with. All right, the next thing we're going to do is the asymptotes. And what's cool about this, I think, is we've already done the asymptotes by finding the domain. So remember, the asymptotes are where we're undefined. So this time I'm going to write equals, because you're allowed to have the equals because we're describing asymptotes. And I'm just going to go ahead and copy straight down. Now, do you have to write this 0? You do not. I'm doing it for learning purposes to make sure everything's real straight for you. All right, now we're working on increasing and decreasing and end behavior. We're looking at the increasing intervals now. So I've marked the increasing just on the top. We have some on the bottom part of the graph, but I'm only focusing on the top right now. So to remind you, because it's not as clear, you're looking for where is the graph going up. So we're going to write the interval of where it starts. I'm going to start in the parent period here. So we start at pi over 2. We're increasing, so it is an open parentheses. We do not include the end value. And then we're going up on this one to pi. So it's only a half a pi interval. So now we're going to look at what is the distance from the next interval or the interval behind. So you can see 1, 2, 3, 4. So that is 2 pi. So I'm going to add 2 pi k, where k is an element of c. Let's see here, 1, 2, just want to double check. And so that's our first interval. Now we have other intervals in the bottom, so we have to break these up because I have to make sure that I'm going to hit these different intervals. So I'm going to separate them. So this one in the parent function starts at pi, and it goes to 3 pi over 2. And then again, you're going to add this portion, but we'll put that in the table. Moving on to decreasing intervals. So let's go back to our big graph. It's easier to see. I'll mark those decreasing intervals now. So the decreasing one is from here to here, and decreasing is from here to here. So again, I'm just looking at the top, and I'm going to put the arrows in just so your eyes will translate that quickly for why it's decreasing. And we will get started. All right, so this one looks like it's starting to decrease from 0 and then finishing that decreasing at pi over 2. the distance between these decreasing intervals. So we're starting here and I go here. You can really see the 2 pi on this one. So this is that 2 pi k again. And then the ones on the bottom, do quickly here. So decreasing, I'm going to mark them for you. So 3 pi over 2, and then we're going down to 2 pi. And then again to show you the distance, you can see half, a whole pi, half a pi is that plus 2 pi k. And you will put that into your table now. So before we move on to end behavior, let's go in and finish the x-intercept and y-intercept, which will be pretty fast. So if we're looking at the x-intercept on the graph, we have asymptotes where the x-intercepts would happen if that was a value on the graph. So that means we don't have any x-intercept for this. So there's none. Likewise, there's an asymptote on the y-axis. We have nothing there that is defined. So again, we have no y-intercept. All right, last but not least, we are working on end behavior. So I want to remind you about the sign graph for the end behavior, so the yellow part. So that's what I want you to look at right now. This is sign here. When we looked at end behavior, what we said was the end behavior was as x goes to positive infinity, what was happening to the y values? The y values were bouncing between -1 and 1. So those were kind of the bounds. Now, let's go back and focus now on the green. When we look at the green, as x now goes to positive infinity, what's happening to the graph is it is, for cosecant, it will never have a bound. And it doesn't matter if we're going the opposite way. There's going to be no y values where that makes sense for the graph. So up here for end behavior, the end behavior does not exist. There is no bound there. So does not exist. And that is your graph for cosecant and all the characteristics. So make sure you're studying this stuff. So secant. So the function of secant is the reciprocal of 1 over cosine. And it works the very similar way as the last graph we looked at. And so for this one, I'm not going to talk a lot. I'm just going to go ahead and write out the items and there won't be any sound.